Okay, let's dive right into this explainer. Today, we're unpacking a fascinating computer-assisted mathematical proof that exposes a massive blind spot in how we measure AI training algorithms. We're looking at a recent paper titled Exact Low-Length Recht and Ré Inequalities, and it essentially proves that we might have been using a completely broken measuring stick to evaluate some of the absolute most fundamental machine learning algorithms.
At the core of this research is a remarkably basic question that underpins countless machine learning systems. When you feed data to a model, imagine you're listening to a music playlist. Do you shuffle that playlist so you hear every single song exactly once before it starts over? Or do you just pick random songs, risking hearing the same track twice while completely missing others? It sounds simple, right? But mathematically proving which method actually trains an AI better is, well, incredibly complex. So, let's compare these two foundational approaches. On one side, we have sampling without replacement. That's essentially shuffling. It forces every single piece of data in a set to be used exactly once per cycle. On the flip side is sampling with replacement. This is pure random independent sampling, where items are pulled completely independently and can definitely be repeated. Now, machine learning practitioners have long preferred shuffling. They know practically that it works better. But pure mathematics? It demands proof.
And for years, theorists leaned on something called the Recht and Ré inequality. You can think of this as their primary theoretical measuring stick to mathematically prove exactly why shuffling might edge out random sampling. It basically asks a technical question: is sampling matrix-valued updates without replacement always at least as contractive, or in other words, as efficient at converging as sampling them independently?
The crucial point here is how this theory is actually measured. It essentially says that if shuffling really is the superior method, it will always show up as having a smaller, tighter mathematical footprint. In linear algebra terms, we call this footprint the operator norm. The theory assumes that the without replacement method should inherently have the smaller operator norm. For a long time, this was just the assumed universal proxy for algorithmic performance.
But here is where things get tricky. AI updates aren't just simple numbers. They're represented as positive, semi-definite matrices. And with matrices, well, multiplication order absolutely matters. They don't commute. Because of this little quirk, products of these matrices can unexpectedly generate negative eigenvalues. So any mathematical proof for this inequality has to rigidly control both ends of the spectrum, proving it never strays out of bounds.
This brings us to a brand new, computer-assisted, and perfectly replayable proof that decided to really test the edges of this mathematical map. The researchers utilized rational certificates and symmetry blocks to map out exactly where the Recht and Ré inequality holds true and where it completely falls apart, specifically by looking at the number of factors or variables in the equation.
And when you look at the breakdown of these results, it's honestly quite shocking. When the algorithm uses 4 factors, the two-sided inequality holds completely. Everything is peachy. But suddenly, at exactly 5 factors, the mathematical measuring stick completely shatters. The upper spectral bound holds, sure, but the lower bound entirely fails. And then, bizarrely, at 6 factors, the lower bound is sharply restored.
Let's zoom in on that failure point for a second. The boundary drawn by this paper shows that the lower bound fails at a very sharp threshold, n equals 5. It isn't some gradual breakdown, it is a hard mathematical wall where the widely accepted justification for random reshuffling simply stops working. To prove the theorem fails at 5 factors, the computer found a brilliant rational counterexample. It generated an eigenvalue of -285/2. This single number sits way, way outside the permitted safe zone of the theory.
Why is that a problem? Well, the math only permitted an absolute minimum boundary of -120. Since -285/2 is -142.5, you can see how that pushes it way past the boundary. This calculation undeniably proves that the inequality definitively fails here. But just as quickly as the mathematical monsters appeared on the map at 5 factors, the lower bound is sharply restored for every combination of 6 or more factors. The paper notes that 6 factors already yield new infinite families where the math behaves itself again. It's a truly incredible mathematical quirk.
Now, what's really interesting is the optimization lesson the researchers uncovered right alongside this failure. You'd probably assume that because the math breaks down at 5 factors, it means the data shuffling algorithm itself is performing poorly there, right? Actually, no. It's the exact opposite.
In this paradoxical metric reversal, running this specific example proves 3 distinct things. First off, reshuffling does indeed produce a larger, worse norm of the expected iterate compared to independent sampling. So yes, the math is failing. But second, it simultaneously yields a smaller expected squared error.
And to top it off, the average objective value actually improves.
This exact evidence clearly shows that our measuring stick is completely broken. On one side, the theoretical proxy, that operator norm, tells us the algorithm is performing worse, but in actual optimization reality, the algorithm is performing better. The mathematical proxy is literally misaligned with the true reality of the algorithm's performance.
The authors hit the nail on the head when they summarize it like this. The Recht-Ré norm comparison therefore measures one form of bias, but it is not a universal measure of algorithmic performance. This makes it incredibly clear that while this inequality measures a specific kind of bias, it absolutely cannot be universally trusted to tell us which machine learning algorithm is actually doing a better job at learning.
And this isn't just some obscure mathematical quirk hidden in a dense paper. It demands that we entirely rethink how we mathematically evaluate new, advanced data ordering schemes in AI. If the traditional norm proxy can rank two algorithms in the exact opposite order of their actual expected error, well, theorists have a major structural problem on their hands.
So, where do we go from here? The paper lays out a really concrete roadmap for specialists. First, they need to figure out exactly when these metrics diverge and identify the assumptions that prevent this reversal. Second, finish mapping the pure math of those six-factor classifications. Third, researchers designing new data ordering models should test their schemes against this newly discovered counterexample. And finally, we need independent verification.
Speaking of verification, a quick caveat. It is important to note that this is currently an unrefereed candidate proof. The internal replay checks pass, but the most critical next step is for external researchers to write a fully independent proof. To be truly credible, the authors note this reproduction should absolutely avoid reusing any of the repository's original orbit encoder or extraction code. They need to build it from scratch.
Ultimately, this discovery leaves us with a deeply provocative thought to consider. If our foundational mathematical measuring sticks, the very proxies we use to dictate AI theory, are sometimes measuring the wrong thing entirely, how much of our theoretical AI benchmarking needs to be rewritten from the ground up? It's a massive question, and it will undoubtedly keep optimization researchers busy for years to come.